thanks a lot for the room open. Oh, okay. All right, can you hear me now? Yeah. Okay, perfect. All right, so this is pretty loud. All right, so welcome everyone. Thanks a lot. Yeah, I've been working on PyTorch for like 1.5 years at this point, and I was like one of the initial authors, although as you can tell from the long author list, it has really been a community project right from the start. And today I would like to present PyTorch to you as this kind of scientific computing library which really embraces some kind of modern features. And you probably have noticed that I crossed out machine learning in the previous slide. And it is true that a lot of the things we do in PyTorch is motivated by the needs for machine learning. This is kind of where the library is coming from. Although this is like pretty well known, and you can find a lot of tutorials for these kinds of applications online. But I would really like to use my position here to kind of show you this different approach that's not noticed quite as often as the other side of PyTorch. And just to start with, I would like to quickly kind of give you the backstory of how PyTorch got into existence, because I think this really showcases some of the values and some of the ideas behind the library that we have and that we take really seriously when developing it. And so the way I started my journey with this kind of package is with something called Torch. And in fact, this was Torch 7. If you Google hard enough, you can still find the website of Torch 3, for example, which has been released in 2004. And in fact, the first report that, like the tech report that was published and that kind of announced the whole package came out pretty much the same year when I went to primary school. So it's been quite a bit some time since then. So it really has some history behind it. But Torch 7, so if you look in here, Torch 3 was really a C++ library. Torch 7 was using Lua as a kind of primary interface to it. And if you think about it, this really makes sense. So Lua is this really simple, fairly clean language, and the simplicity also makes it extremely fast. And it has really good like foreign function interface to C. And so as an evolution from C++, where the authors probably had a lot of existing code, Lua seemed like a fairly straightforward choice for it. It's really popular, for example, for embedding kind of scripting in already existing applications. So for example, you can script games in Lua. And yeah, so I basically went to the university. I wanted to start learning machine learning. And I looked into a few other packages, and Torch really seemed pretty much perfect for me. And something that I really loved about it was that it was so ultimately hackable. Like it was structured really nicely in this high-level language, and you could pretty much go into the internals of the library and start replacing existing functions with your own callbacks and kind of seeing how the values change. Print, poke around. And this was really a valuable learning experience. Like you can really get a really good feel of how the library works. And I thought this was amazing. And so we wanted to keep a lot of this. But at the same time, so I was a huge fan of Torch. But yeah, at the same time, if you were to go onto Reddit, for example, onto the machine learning Reddit, and people were asking questions like, what language should I basically pick up, or what machine learning framework should I use if I want to get started with? And basically all the top voted answers were like, just go with Python because everything is in Python. And yeah, so I really wanted kind of to show Torch to like, basically make it more widespread because I thought it was great. And just to give you kind of the idea of how the machine learning landscape looked back then, so Torch was kind of so Lua is this really simple language and it hardly has any standard library. So Torch pretty much had to implement a lot of the things that are in Numpy, so it's like an ND array library, plus some helpers on top of this to make training of machine learning models much easier. And so the kind of more popular alternatives were Caffe, which like the way you were specifying how your model worked was by writing out this kind of JSON-like thing, although this is a text representation of Google Protobuf, I think. And so the way you would write out your model would be basically by specifying those layers, and you would basically give them types as the kind of operations they do. And you would also call, like, give all the inputs and outputs to individual operations names. And this is what you would use to kind of connect them up into the whole computational graph. And then you would kind of hand it over to Caffe in this format, and it would optimize it, it would analyze it, and then it would like have the whole training loop embedded inside. And so Caffe was really popular in vision research, and this interface even really made sense because it was kind of easy to, you know, load and analyze. And on the other hand, a lot of the research back then, Caffe was really popular in vision research, where kind of the models were pretty, like, you know, they were basically a straight line of ops. And so it was fairly easy to also specify them in this format, although it doesn't scale quite as well to more complicated things. And the other alternative was Theano, and Theano actually had the Python interface, and I think this one was the most popular. And so the way Theano worked was by kind of embracing symbolic computation. So first you were basically declaring what would be computed, so you would specify basically placeholders in your computation. So in here you would say that there will be some input called x, and then it has all of the operators overloaded, and you also get a lot of the math functions that are there on Numpy, except implemented in Theano. And of course this doesn't just do anything just yet, it pretty much only records that you would like to do the operations. It doesn't perform them because you don't have the data. And once you did that, you basically get to step 2, which is to tell Theano, okay, now give me actual function that given those inputs will compute those elements as outputs. And then Theano would go into the background and kind of start thinking, and it would also take this, realize it as a graph, start analyzing it, optimizing, and then actually emit either machine code for CPU or for CUDA, because basically all 3 of those frameworks supported GPUs. Like GPUs were really something that helped deep learning take off because they're really well suited towards these applications. And so one downside was that this compilation, since like especially compilation for GPUs is really expensive, so basically this line could even take minutes if your graphs were larger. But then you would basically get a simple callable, so then you really have your regular Python code that runs just as you would expect it. One extra downside of this approach is that what do you do in this first step? So if you would like to, for example, create a graph that would be kind of agnostic to the size of your input, like if you're processing text, for example, sometimes you want to loop over the text, right? And it's not a fixed size length loop. So if you were to just stick a Python loop in here, this would basically kind of inline the body as many times as the loop ran, and also like you don't really have any way to get the length, like a fixed length that you can embed there. So you would basically have to resort to some special operators. So there were some looping operators where you're basically given the body as a function, and then Theano could embed this. But this is basically diverging from Python semantics, right? Python is really this really convenient and nice general programming language, but in here you're basically using it to meta-program some other application. And so yeah, these were kind of the alternatives, and they were working really good. But I think there was still a lot of value in how Torch worked, and it so fortunately happened that at the same time, there were pretty much a few refactors going on in the code base that were meant to kind of rip out the Lua part from the actual kernels that did the math inside the library. And so, you know, this seemed like a pretty good moment. I started talking with Sumit Chintala, who was a maintainer of Torch back then. And, you know, after a few months, basically, PyTorch emerged. And yeah, and I think this journey kind of gives me a few ideas. Like I spent some time working on this, which really highlight like what are the strengths of Python and scientific computing. And so the first one, it's something that I think Python really uses to its great advantage, is the Pareto rule. So if you were to, so one way to apply this to scientific computing would be to basically say that probably 80% of the runtime of your computation is spent in 20% of the code. And if you're doing scientific computing, it's pretty likely that this 20% of the code is like heavily optimized C code and sitting deep inside some library. And what this means is that even though Python interpreter might be a lot slower than the Lua interpreter, you pretty much don't lose so much speed because this is like this kind of glue that's kind of irrelevant in the performance between those library calls where you really spend the time. Also, if you're doing some data exploration or some research, because that's a fairly popular use case, for Torch, then planning is really hard. And so this is something where the Python ecosystem really benefits you a lot. Basically because if you want to use a new library, you probably pip install it, and it's there for you, and basically in minutes you can start integrating it into your application, and you can immediately start getting feedback on whether it's useful for you or not. In Lua, this would be probably different. So as I mentioned, the scientific community is much smaller in Lua. And as such, you would probably need to kind of drop into the C level, find a C library, bind it, debug the bindings, test them. And of course, this basically costs you hours, and you're not even getting any signal whether the library is actually useful for your use case or not. Also, Python is really expressive. So one anecdote I have for this is basically one of the really core parts of PyTorch was initially written in Python. And it was basically like 70 to 100 lines. Then we started profiling PyTorch and comparing it to LuaTorch. And in fact, it turned out this part really is in the hot path. It was executed pretty much every time you did anything. Pretty much you did anything with Torch. And so the overhead of the Python interpreter really started to show up. As such, we decided to move the code to C, basically. And once we really did this, it basically blew up to over 1,000 lines. So it's kind of pretty amazing what you can do in just a few lines of Python. And finally, something that's not often, that people don't often realize, I feel like when choosing dependencies, is that you shouldn't really only optimize for performance. The cost of development is basically really matters, and it might not always be important to kind of optimize everything as much as you can, and it sometimes might be beneficial to actually pick things that are slightly slower than the others if the interfaces are really nicer and they let you move much more faster and are much more intuitive and much easier to actually debug. That kind of wraps up the story part. Now I will kind of move on to the second part of the presentation, where I would like you to actually show how PyTorch looks like. And so I mentioned that LuaTorch kind of was basically working like Numpy plus some higher level helpers. But of course, Python already has Numpy, and as such, it would be pretty. It might not be just a good idea to re-implement everything all over and try to get everyone to switch. And of course, that would be really silly. And PyTorch is not meant to do that. It's really meant to kind of augment this and to integrate naturally with the environment. And so the first feature I would really like to show you is kind of the Numpy integration. And so just to kind of calm you down that you're not really getting locked up in another completely separate ecosystem. So the main package for PyTorch is called Torch. And the way you, for example, can use it, and here we allocate a 2x2 array. The interface is fairly simple to Numpy. And then when you actually want to get a Numpy array, so arrays in Torch are called tensors, which you can see in here. And if you call that Numpy, then you basically get a Numpy array that has exactly the same content. And if you want to go in the other direction, you call torch.fromNumpy, and this gives you back a Torch tensor that has the same content. And so you might be slightly worried in here because the arrays often manage quite a bit of data, and copying them would basically destroy the performance of any of those scripts. However, it so fortunately happens that PyTorch and Numpy use exactly the same format of the arrays. And so these functions basically have to modify only some metadata to make these packages understand each other. but the actual data is shared. So if you were to, for example, change x in here, like add to every element 1, but just modifying the memory in place, then y would also see the change. And if you were to change y, then both x and z would change. So there is really no copying. The cost is basically on the order of nanoseconds. And PyTorch tensors also implement the kind of Numpy array interface, and so you can pretty much pass them to most Numpy and SciPy functions as they are, and they should just work like this. And now one of the features that I feel that Numpy is really missing currently is the accelerator support. So a lot of us already have accelerators in our computers. GPUs pretty much support general purpose computing for some time. And this array-oriented kind of idea of specifying the programs, like in Numpy, basically fits them extremely well because there's a lot of parallelism in those operations, and they're heavily vectorized. And so PyTorch currently supports CUDA GPUs from NVIDIA, but we already have a pull request, and we're already working, and we're pretty close to get AMD GPUs also working. And there's also a bunch of other accelerators that are kind of branding them as accelerators for machine learning. But again, to be honest, like a lot of machine learning is basically matrix multiplication, and a lot of other things is also matrix multiplication. And so they might turn out useful as well in some way. And just to give you a feel of how this works, so this is basically a CPU-only script. You basically can write this out, and this will add those 2x2 random arrays on the CPU and print them. Now, if you want to run this on the GPU, you basically do something like this. So just disregard the first line for now. So all the constructors, like this one that gives you this random array, they take a device argument that basically tells Torch where to put the actual data. And alternatively, if you don't specify this, this part will basically give you a CPU array, but then you have a to function that lets you actually copy it to a different device. So this is fairly easy. And then the interface, of course, stays exactly the same. So it's really easy to actually write functions that can run on any kind of device. And that works pretty seamlessly. And also, so what the first line does, it basically checks if there are any CUDA-enabled GPUs in the system. And if they are, you will be using the first one of them because, of course, you can have multiple GPUs. Like people even have 8 or 16 plugged into the same computer. And so PyTorch also enables you to run computations in parallel on multiple GPUs if you have a lot of data. And otherwise, we just fall back to the CPU. So this makes the script pretty much generic, and it will run on any computer, except that if you have GPUs, it will probably run a lot faster. And another feature that's really built into the core of PyTorch is high-performance automatic differentiation. And this is especially important in machine learning, but this is pretty heavily used in other domains like engineering or physics or finance. And so as an example, you can take, so this is a gradient of the temperature in the world's oceans, and this is coming from the MIT GCM project, which is meant to kind of simulate the evolution of the conditions in their project. They're not using PyTorch, although a fairly important part of the process is automatic differentiation. And the use case for machine learning, but not only, is that if you have an optimization problem and it turns out so that the function you want to optimize is differentiable, then it's basically a no-brainer, right? Like the gradient basically tells you the direction where the function is increasing the fastest in any particular point you're at, and the opposite direction is the direction where it's decreasing the fastest. So you can actually do small steps according to where the gradient is pointing. And as you can see in here, you will start climbing this ridge, for example. And PyTorch also has a built-in package that implements multiple gradient-based optimizers. So if you, again, have a differentiable function, it's fairly easy to actually put together something that will use this gradient information to find a better solution to your problem. And so the way this works is pretty much every array in PyTorch supports automatic differentiation. It's just disabled by default because it requires some extra bookkeeping, and it also adds some extra memory pressure. But the only thing you need to do, so you still write out your functions just as if you would write them out normally, as if you weren't using automatic differentiation at all. So here we have some polynomial. You can see that there are no changes pretty much. And the only thing you need to do is to mark the things you will be differentiating the outputs with respect to as something that requires the gradient. So PyTorch normally only can compute gradients. You can, of course, compute Jacobians using this, but this is like the most common use case where you actually want to optimize a scalar function. And then you can compute this with this array that actually requires grad, and then you can ask Torch to actually give you the gradient of the output of this function with respect to this x. And this will return you another array, which you can verify in here that the gradient matches what you would expect. And this is, of course, differentiable as well. So you can also take higher order derivatives if this is what you need for your use case. Another thing, so initially you will probably be working with some small data sets to kind of try out different approaches, but sometimes you really have much more data, and it becomes increasingly important to kind of have a good data loading pipeline so you don't stall the whole script. And the way PyTorch solves this problem is there's this data loader class that basically takes in any Python object that kind of behaves like a list. So we need to be able to get its length, and we need to be able to use the native indexing operator with integers from 0 to length to get the elements. And this is your whole data loading pipeline, basically. So you can tell it to actually use multiple processes to use to load the data in parallel without stalling your script and blocking the GIL. It does support batching. This is especially important for the GPUs because for small arrays, you can basically think that the cost of doing the compute on the GPU is constant, and you need enough data to actually make the array significant enough for the GPU that it actually has to do some work. And it also supports shuffling. When you do some kind of optimization, it's often important that you visit kind of different examples in different order every time you start over to iterate. But if you turn this to false, the order is entirely deterministic. We ensure this even if you're using multiple processes to load the data. So you can also think of this as a kind of dumbed down map reduce. This step is basically map where things are happening in the workers independently. Then there's of course no shuffle, but then the data actually gets back to your main process, and you can do some compute and actually combine the data that's coming from the different sources. If you have some kind of pre-processing, you probably put it into the dataset logic, so that this doesn't really block the main process from doing useful compute. And then you just iterate over the data loader, and this will prefetch the data, so the loop is extremely busy basically. Also, something that's relatively new, PyTorch does support easy C++ extensions. So this is the code. I won't be getting into the details, but basically there is something called a Jacobi method, which is for solving linear systems of linear equations. It might not be the best, but let's say that for some reason you're actually using this. And so you're passing in the coefficient matrices and then tell how many iterations to run. And basically, given some initial conditions, we can do some pre-processing on those coefficient matrices. And then we start from a candidate solution that's all zeros in here. And basically, by doing this iterative matrix multiplication and addition, under some initial constraints, we have a guarantee that that the candidate will actually converge to the real solution to this system of linear equations. And if you were to write this out, and actually it would turn out that this is a pretty heavy hotspot in your computation, then you can basically rewrite your function in C++, and it would look like this. So if I switch back and forth, you can see that it's pretty much a syntactic difference between languages. And right now we actually have a really simple no template C++ API that exactly matches what we have in Python. So it's really kind of easy to go back and forth. And we're relying on PyBind to actually bind those functions to Python. And as such, this is pretty much everything you need to expose this function. Of course, this doesn't even need to take PyTorch tensors. You could it automatically converts Python dicts to like standard library maps, it automatically converts lists to standard library vectors. So it's really easy even to use this to bind your existing C++ code. And then you'd basically change your Python code to something like this, which tells Torch where to find the files and like what kind of extra compilation flags to use. And it will also cache this, so it's not like compiled every time you run this. And this loads the thing you've defined here. So this is like a Python module that's defined in here using this macro, and it has this Jacobi solve method. So you basically take this, and all your remaining code stays exactly the same. Everything works exactly as you would expect. So this is fairly easy. And also, something I didn't mention previously, like by going to C++, you're not really using anything. So for example, this iterative method is actually differentiable with respect to B. And if you were to use autograd package in here from Torch, this would basically work just fine. So it's not really breaking anything. And also something I didn't mention about autograd previously is that it also supports differentiation through pretty much arbitrary Python constructs. So if you have a for loop, like a native Python for loop, a while loop, a generator, a coroutine, whatever, autograd doesn't really care how did you compute something. It only cares about the actual quantity that you computed. So you can really write native Python code just as you would normally do, and this will all work just fine. And the next thing, PyTorch actually has a built-in profiler. So this is how you actually discover that certain things are bottlenecks. And the API is fairly simple. It's not a general purpose Python profiler, so it won't kind of give you line-by-line information. It only records the PyTorch operations that did happen inside on those arrays. But thanks to this is actually really efficient. Like it really hardly adds any time to the actual compute, and so the output you get is not skewed, because like a lot of the profilers, if they add overhead, then basically you get some false numbers, and this is really, and then it's really hard to reason about those traces. And then there is so you basically wrap something in this context manager, and this will automatically turn the profiler on at the beginning, turn it off at the end, and then you can either analyze the results directly in Python, or there is this one nice little method called export Chrome trace that will create this file, and then you can open up the Chrome browser, go to the tracing tools, and this is what you get. So you get an exact timeline of when any given operation was executed. So this is actually a profile from the C++ code. This also works for C++. So this is the Jacobi method. You can see the matrix multiplication in here, and then there is a little add in here. So you can see that a single iteration for that benchmark took like 25 microseconds, and you can see how tiny are the actual individual gaps between the ops, which makes sense, right? Because it's C++, so there is no interpreter overhead. It's basically an assembly loop, and this profile actually shows that the C++ version is 2 times faster than the Python one. But you of course can like start dropping only the hot functions while leaving everything else in Python without any cost, basically. Then there's also distributed computing. Once you get to even larger data that you can't process at a single computer, I won't really have time to get into the details of this, but basically for those interested, PyTorch supports an MPI-like model, which basically means that you have a group of processes, possibly on different computers, but they can even all be on the same one. Everyone runs exactly the same code. It's just that every process can see its own identifier, and based on this identifier, it can take different roles. It can basically take different branches through this code. And what we cover for you is automatic discovery. So if you have any shared resource like file system, or everyone is on the same network, you don't even need to hard code any IPs. Like each process will basically find all its peers by itself. We do initialize everything. We have all the both simple communication functions like point-to-point, send and receive, and also some more complex collectives that are an MPI like broadcast, where one process sends something to everyone else, and this is implemented in a much more efficient way than a naive for loop, of course. And this is basically also a wrapper around multiple backends. So currently we do support 3 backends out of the box. So you write your Python code once, and then by changing a single argument, you can basically completely change the actual implementation used for exchanging the data over the network. So currently we do support MPI, pretty much any implementation you would like to. There is Glue, which is a library developed at Facebook that's really optimized. And there is also Nickel 2, which is GPU only, but it's developed by NVIDIA. And as such, it's also really efficient. And the next thing is automatic optimization. So you can think about this basically like Numba, but for PyTorch, except that we never really want you to drop to the actual scalar level of computation. This is more meant to optimize the actual array level stuff. So there is a module called TorchJIT, although I don't really want to talk about this right now. It's really a project that's in progress. So this is something that's really hot in the machine learning kind of community right now. And we're working on this actively, but this is not ready just yet. We hope to release it in the upcoming months sometime. And finally, PyTorch is a really fairly young library, and we think of it as a clean slate that really builds upon some of the best practices we've seen. So actually, if you look at the Lua torch, PyTorch is not very similar to what was there. We actually changed a lot. We took some time to actually explore different approaches that people use, and there were packages like Chainer or Autograd Autograd was actually a package from HIPS from an MIT lab as well. And we really liked what they do, and we wanted to integrate this kind of into a single library where this is heavily optimized and where this plays well with kind of all other features. And there are some other things that we really embrace. Like PyTorch really is community first. So it is true that a lot of people that are working on PyTorch full-time are employed at Facebook, but it's really that we do all our development in the open. We use GitHub as our source of truth. We use issues to communicate. We use pull requests basically for every single feature. There is no other control version system we use. And when we were designing it, we're really trying to build a tool that's generally useful for everyone. And so if you have any feature requests, if you have any feedback, we really welcome this, and we will be surely taking this into account in the design process. Also, we have this open world assumption because that's basically what enables this hackability. Like, we never want PyTorch to kind of enforce anything on you. It's like if you have, it is not a framework, it is a library. Basically, everywhere where you think you would benefit from this, you can use it, and it's you who dictates how you actually use the library, not we telling you how should you structure your code and what should it do. Also, we never want to go down the path of metaprogramming because Python is really this great general purpose language that's very convenient, and we really want to kind of embrace its original semantics. And so you could see kind of this when I was showing the data loader, but like we never want to impose artificial constraints. We do really think that you should be able to do pretty much whatever you do as long as it makes sense. Just at the end, I also won't have a lot of time to show this, but PyTorch already has started to create its own community. We do have a lot of community projects. I will only have time to kind of mention two of the bigger ones. So on the right-hand side in here, you can see a logo of Pyro, which is developed at Uber. And it's a probabilistic programming language, basically for Python, that also supports pretty much any Python construct you have. And so if you're into probabilistic programming, you should really check it out. On the other hand, on the left-hand side, this is a project called Tensor Comprehensions. And so Tensor Comprehensions isn't really reliant on PyTorch, it just has really great bindings. And this is also a project that's coming from the Facebook AI research labs. And basically the idea is that sometimes there are some linear algebra operators that are missing from all the libraries that you see. And so what Tensor Comprehensions does is they define kind of a small programming language that's heavily similar to the Einstein notation. So for those of you who don't know this, because it's not very popular, basically you can write out matrix multiplication in a single line of code. You can write out convolution over multiple dimensions, which is really popular in machine learning as well, also in a single line of code, but of course it will consume more complicated scripts as well. But usually they range, around let's say 5 to 10 lines of code, so it's not much. And then basically this will take this code, analyze it, and it will automatically emit both GPU or CPU kernels for this code, which are heavily optimized. So if, if writing something at the array level would involve some really advanced indexing or something where you have, or you would basically have loops that you can't really vectorize, then this might be an answer that also automatically gives you code that has really good performance and that can also execute on the GPU. And it will basically give you, again, a callable in Python that can run on that can take PyTorch arrays and will also give you back PyTorch arrays with the results. And so as such, I really don't want to replace anything. I rather would like to think about PyTorch as kind of the supercharger that adds some more modern features to your existing Numpy workflows. So if you're basically using Numpy as part of your work, you might really want to check this out because we're really structuring it as a general purpose library as well. And just at the end, we do get a lot of support from different users. We do have a lot of community. PyTorch is already supported by a few of the large companies, and we also have quite a lot of academic users, and it's pretty heavily used for research and machine learning. It is as I mentioned, it is a fairly new package. So it has been released like a year ago, pretty much. But we've already seen like 1 million downloads. We have packages both on Conda, which is kind of our preferred package manager, mostly because we do depend on some extra C libraries that do the math, like Intel MKL, to make CPU processing faster. We do have plenty of, but starting from the next release, which will probably happen sometime on Monday, we will have pip packages as well. You could install PyTorch from pip. It's just you would have to go to our website and like use a special link. But thanks to the new pip infrastructure, which is great, we can finally start putting our packages there as well. So thanks everyone who works on pip. We do have plenty of community repos. Online we have pretty active user forums when you can go and ask for help. We also have people from our core team who go there and answer questions if you have any problems. And currently our GitHub counts over 400 contributors. We always welcome more contributors. As I said, if you have any ideas or feedback, just open issues. We're reading them pretty much daily, so we'll try to get to you as soon as we can. And that's basically everything I have for today. So thanks everyone for coming, and I hope to see you on GitHub or on our forums.
Right, so we have time questions. Any question? Yeah.
Thank you for presentation. You spoke about CUDA and NVIDIA GPU, but you can easily test your code also on some notebook with Intel GPU on it, and there is some optimization for this situation.
Mm-hmm. So we don't support general GPUs like Intel GPUs usually. I think they do support OpenCL, although AMD is kind of now taking a different direction, and they're not so heavily reliant on OpenCL. They are actually writing a separate compiler that can actually take CUDA code and run it on AMD GPUs, and this is kind of the approach we're taking. Just because we have a lot of CUDA code that we inherited from those older libraries, because it's really heavily optimized and it works really well. And as such, it really is a huge investment to actually add support for other architectures. So this is what we're using for AMD GPUs in particular. But usually, as I showed before, you can have this single if statement, and basically your whole script can run on the CPU as well. And so it should be also just pretty easy to try out scripts on your local computer as well. That's what I do usually.
Any other one?
There is one question.
Oh, sorry. Yeah.
PyPy.
Yeah, we don't support PyPy just right now. It's like we have a lot of C code, so we have a lot of C bindings, and so we're just using the C Python API at the moment. Uh, Not a lot of people use PyPy, so unfortunately it's not like, there's not a lot of incentive. But if someone has, ideas to kind of make it easier to support both, then we're open to talk about this.
Is it a port on Windows? Is Windows supported, or do you mean are you planning to make a porter for Windows?
Yeah, so we do have one person from our community who's amazing and who basically, our code was working only on Linux, but he started like sending us pull requests, and he like patched all of the code that was not supported on Windows. And so starting from this release, we actually have CI running on Windows. We make sure we don't break this, and probably on Monday we'll have Windows packages appear as well. So this should be really easy to install soon.
Just one question about the JIT. What do you plan to do with the JIT?
It's basically a bunch of optimizations that you can do at array level. So one simple thing that's fairly easy to understand is basically when you have a few like pointwise operations, right? So it's not like matrix multiplication where a lot of elements interact with like between each other in different arrays. When it's something like add, where basically you're like adding two numbers at each element, then if you have a few operations like this chained, then like it's fairly inefficient to do it in the naive way, right? Because you need to like allocate temporary after every single operation, just because from the level of our library we don't really know what will be the next operation that you will execute, right? So Python doesn't tell this to us in any way. But if we have some upfront knowledge, if we know what this will be, then we can, for example, also generate like CUDA code that's like a single column that computes all of those things without any intermediates. But then the compilation is fast because it's like a single, small, simple thing, right? So it doesn't really add a lot of overhead, but sometimes it really makes a fairly huge difference. So that's kind of an example. But there are a few other things that we're targeting as well.
Okay, so I think we're done. So thank you very much, Harlem, again.